Consider a function of time whose rate of growth at any time is directly proportional to the value of the function. Well, we want the rate of growth of our function, which is dy, and it's a function of time, so that's dt, to equal, well, it is directly proportional, so it's equal to some constant k, times the value of the function, which is just y. Here we have a very specific type of differential equation that is defined as the rate of growth, dy dt, being directly proportional equals k times the value of the function at that time t. Let's solve this differential equation to see what type of function we are talking about with this particular property up here. So the first step to solving a differential equation is to separate the variables. We're going to get the y on the left-hand side and the dt on the right-hand side. So I'll divide both sides by y, and I'll multiply both sides by dt. So here I have 1 over y dy is equal to k, some constant, times dt. Well, at this point, I'll want to get rid of my dy and my dt, and to do that, I can integrate both sides. The antiderivative of 1 over y is the natural log of the absolute value of y plus c, but of course I'll move that plus c to the right-hand side as we have done before. The antiderivative of k dt is kt, and I'll put my plus c over here on this side. Now I want to get y alone, so I'm going to set both sides to be e to the side. So I'll raise both sides to the power of e, and I get e to the natural log of the absolute value of y is equal to e to the kt plus c. Well, e to the natural log of the absolute value of y, e and natural log, they cancel out. And that gives us the absolute value of y is equal to this e to the c here. I can move in front, so this is e to the c times e to the kt, and I'm allowed to do this due to one of our properties of exponents. When we multiply a common base, we just add the exponents. We have kt plus c. And of course, we can always break it up and go backwards as well. Now, e to the c is always going to be positive for any c. And e to the kt is also going to be positive for any k and any t. Now, the absolute value of y, apparently from our right-hand side, is always going to be positive. And so we don't really need this absolute value. It's completely extraneous. So let's rewrite our function as y equals e to the c. Well, c is just some constant, and e is about 2.71, so on and so forth. 2.71 to some constant is just another constant, and that's times e to the kt. And this right here is the general formula for a function whose rate of change is directly proportional to the function value at any time t. K is called the constant of growth. Now you'll see here that this is an exponential function, ce to the kt. This exponential function follows the property that the rate of change of the function is directly proportional to the function value at any time t. Now let's take a look at our c, our constant c, and let's determine what c is in context with exponential growth. Now consider that y is either a population of amoeba, or it's the amount of money that you are getting out of your account, or whatever y is, it's some function value. Let's take a look at what c might be. To do that, let's plug 0 into t. So when t is equal to 0, let's solve this particular equation. Here we have y is equal to ce no matter what k is, times 0 is always going to be 0, and e to the 0 is 1, so that means that y is equal to c. Well, this tells us that c is equal to our function value when time is equal to 0. When time is equal to 0, our function value is our initial function value. It's what we begin with. So we can rewrite c as y naught. And y naught represents the initial value of the function. So if you're putting money into an account, it's the initial amount of money that you put into the account. If you're looking at the growth of a population, it's the initial population at time t equals 0. And this right here is the general formula that follows the above property.